Now is given a matrix. We want to consider certain subspaces associated to a matrix. In particular, what we look at in today's lecture would be row space, would be column space and null space, right? And in our next lecture, we will look at left null space. Alright, so I have a matrix that is denoted by capital A, right? Okay, so a matrix is denoted by capital A. This is a m by n matrix. M is the number of rows and n is a number of columns, right? Okay, so for example, this matrix here, right? The m is equal to 2. You have 2 rows, and then you have the n is equal to 2. It's 2 columns, right? This matrix here, I mean, it's an augmented matrix, right? This one here, what it would have is this has m is equal to 3 rows over here and 1, 2, 3, 4, 5 columns, right? N is equal to 5 columns, right? Okay, so I have a m by n matrix, right? Well, what are the rows of a matrix? The rows of a matrix, so for example, for this matrix here, you have 2 rows, right? Your first row is 1, 2, and the second row is 0, 1, right? Okay, so this 1, 2 here, right? What I can regard this 1, 2 is I can regard it as being a vector, right? In two-dimensional space, right? So this is, I'm regarding your first row over here as a row, I'm regarding this first row over here as a row vector, right? And this row vector belongs to R2 because it has 2 entries in it, right? And likewise, this second row over here I can regard as a row vector also belonging to R2, right? Okay, so why it's 2 over here, why this vector here belongs to R2 is because you have 2 entries over here in this row vector. And the number of entries that you have in your row vector is actually equal to the number of columns in your matrix, right? And in this case, the columns, you have 2 columns in this matrix, right? Okay, so with this matrix A, I have 2 rows, 1, 2, and 0, 1, right? I can regard each of those rows as a row vector belonging to a 2-dimensional space, right? And the first thing I can do is these vectors here, what I can do is I can take the span of the row vectors, right? So remember what span of vectors means, right? It means that you're going to take all possible linear combinations of the vectors, right? So in other words, it's your, in this case of 2 vectors, it's your first vector times a constant, second vector times a constant, right? And this notation here means that you're free to vary the constants C1 and C2 as you please, right? And when you vary the C1 and C2, right, what you're going to get is you're going to get a large collection of vectors, right? And these vectors are in fact going to sweep out a subspace of R2, right? And in this particular case, the subspace of R2 that we're going to get, right, is in fact just R2 itself, right? So recall the definition of the span of a set of vectors, right? So if I have a finite set of vectors like this, right, then what your span is set of all linear combinations of the vectors, of the u vectors over here, right? So I'm doing the same thing here, right? These are the u vectors if you want. This is u1 and u2. Taking the span of them means that I'm taking linear combinations, all possible linear combinations of the vectors u1 over here and u2 over here, right? So I'm using this definition, right, for span. Okay, so row space of a matrix is you take in the rows, right, regarding the rows as being vectors in Rn, and where n over here is the number of columns, right? Okay, so this vector over here 1, 2, right, notice it has 2 entries over here, and it has 2 entries because there's 2 columns, right? First column and second column, right? So this is a vector of Rn where the small n is equal to 2, right? Okay, so this vector belonging to R2, this vector belonging to R2, I take the span of those 2 vectors and that gives me row space of A, right? Alright, okay. Now if I have two matrices, right, of the same size, so both of these are m by n, right, and that they're row equivalent, right, which means that I can apply a sequence of row operations to A and that will get me to B, right? Some sequence of row operations will convert the matrix A to B over here, right? Alright, so if I have two row equivalent matrices, right, then the row space of the matrices are the same, right? So if I go from A, right, so if I have A, apply row operations to get B, consider row space of A and consider row space of the transform matrix, right? And it turns out that the row spaces are actually going to be the same, right? That's because you got B from A by using row operations, right? So the idea is that your row space is not changed by using row operations, okay? Right, so let's see a simple example of that, right? So consider, say, this matrix here, A, which is a 3 by 3 matrix, right? And I'm going to do one row operation on A, right? And the row operation that I'm going to do is I'm going to exchange two rows, right? So notice I exchange row 1 and row 2, right? So when I switch row 1 and row 2, I get the 4, 5, 6 come in on the first row and then the 1, 2, 3 on the second row, right? Okay, so you want to notice that the A and the B are no longer same matrices, right? But it in fact satisfies this condition in theorem 3.3, right? It satisfies the condition that A and B are row equivalent, right? Because you can go from A to B by this sequence, right? This row operation over here, right? So you can go from A to B by this row operation, right? So you have a sequence of row operations taking you from A to B, right? And therefore A and B are row equivalent, right? Okay, so what I want to show is I want to show that the row space of A is equal to row space of B, right? Okay, so this was just simply an example of this proof over here, right? Or this theorem. Okay, so, well, what's the row space of A, right? Well, what you're doing is you're going to take the rows of your matrix A, right? And you're going to form vectors from those, so 1, 2, 3, right? And then the second row over here, which is the 4, 5, 6, will give you a next vector. And then your third row over here, 7, 8, 9, will give you, okay, so the 4, 5, 6 give you a second vector, and the 7, 8, 9 give you a third vector, right? Right, okay, and you use your definition now. So your row space is the span of those row vectors here, right, that are formed from the rows of your matrix. And span is a set of all linear combinations of these three row vectors here, right? And we just saw that, so we're just using a definition of span over here, right? Okay, so what I want to justify is that the row space of A is equal to the row space of B, right? So if I want, I could start on this side, start on the bottom, right? I want to show that row space of A is equal to row space of B, right? So I can do it in a somewhat unorthodox fashion by saying, well, alright, row space of A, it's by definition span of the rows over here, the row vectors, and this is my definition of span here, right? And I can start with row space of B now, right? Now, what is row space of B? What I'm going to do is I'm going to take your row vectors 4, 5, and 6, 1, 2, and 3, 7, 8, 9, form, and then take the span of those, right? And the span of those is by definition of span is equal to this third line over here, right? And now to justify that the row space of A is equal to row space of B, right? All I need to do is justify that the second line is equal to the third line, right? Okay, and notice if you look at this, what you're doing is you're adding vectors here, right? Now, the addition is, you can change the order of the addition, right? That is a property of the vector space, right? Okay, so I can change the order of the addition and put this 4, 5, 6 out in front over here and put the 1, 2, 3 in the second position here in the sum, right? And you want to notice that this, so I have equality going from here to here from the fact that I can rearrange the order of the addition in a vector space, right? And this here, this third line over here is equal to row space of B, right? And this second line over here is equal to row space of A, and that will show you that the row space of A is equal to the row space of B, right? Alright, Okay, so our next sort of quick sort of overview way to see this, right, is, well, what's row space of A? It's the set of linear combinations of these three row vectors, right? And what's row space of B? It's the linear combinations of this of the three row vectors 4, 5, 6, 1, 2, 3, and 7, 8, 9, right? And the point is, if you take in linear combinations, it doesn't make a difference what order you have these in, right? So if I have this 1, 2, 3 vector first and the 4, 5, 6 second, right? Or if I have the 1, 2, 3 second and the 4, 5, 6 first, right? You get the same span, right? So you get the same row space, right? Okay, and why you get the same span is because, well, you see from your definition, what you're going to be doing is you're really just adding the vectors. So if you reverse the order, you still get the same sum, right? Okay, so this is an example of two different matrices, right? But they're row equivalent as stated in theorem 3.3, right? And they have the same row space, right? And how you go from this matrix A to this matrix B is by a single row operation, which is switching two rows, right? Now, so what that shows is I go from one to the next one by switching two rows, right? The row space doesn't change, right? Now, if I went from B to C, right, by switching two rows again, right? Well, to go from A to C, I'd need to swap two rows, right? Swap two rows, and I need to do that twice, right? But the row space doesn't change from A to B, and the point is it doesn't change from B to C, right? Okay, so overall, if it doesn't change from A to B and it doesn't change from B to C, then it means it's not going to change from A to C, right? Okay, so the idea of how you would prove this is you prove that if you to go from one matrix to the next matrix, if you use a single row operation, then the row space doesn't change, right? And we see an example of this if we just switch two rows, right? If we switch two rows, then the row space doesn't change, right? And then likewise, you can show that if you multiply a row by a non-zero scalar, right, going from this matrix to a next matrix by this type of row operation is not going to change the row space, right? So you can try cooking up some examples and seeing for yourself that the row space isn't going to change, right? Or if you want, you could look at this proof, right? And the proof will show you that if you go from here to here, right, by using row operation C times row I, right? And the proof is in fact over here, right? Okay. If you multiply a row by a non-zero scalar, then the row space isn't going to change, right? Okay, and likewise, well, this one is a little more complicated, but it's the same idea that if I have a matrix A and I apply this row operation to get a new matrix B, right? Then the row operations is not going to change the row space, right? The row space of this one is going to be the same as the row space of this one, right? Okay, so the idea is that if you have a matrix A and you do a single row operation to get a new matrix, whether the single row operation is of this type, or this type, right? The row space doesn't change, right? And what that means is now if you do a sequence of row operations, each time you do a row operation, your row space isn't going to change, right? So even if you had a long list of row operations taking you from one matrix to the next matrix, at each step the row space doesn't change. So overall the row space is not going to change from your start matrix to the end matrix. So that's really how this theorem 3.3, that's the idea of it, right? Okay, so let's look at theorem 3.4, right? This is saying that if I have a non-zero matrix that is RREF, right? And I have an example over here. This matrix is RREF, right? Is reduced row echelon form, right? Your zero rows on the bottom, right? The pivots are all equal to 1. The pivot is the only non-zero element in the column, right? And the pivots are coming down like this, right? So if you have a pivot in a lower row, right, then it's going to be in a column to the right, okay? Or to put it more colloquially, pivots are going to come down on a diagonal like this way, right? Okay, so this is an RREF matrix, right? if you have an RREF matrix, what this theorem is saying that the rows of the RREF, the non-zero rows of the RREF, are linearly independent, right? Okay, so this is an RREF, and what are the non-zero rows, right? The non-zero row would be the first row over here and the second row over here, right? Okay, and I want to show, at least in this example, that the non-zero rows for this RREF are going to be linearly independent, right? So your first two rows here are going to be linearly independent, right? When you form row vectors from them, right? Okay, so how do we show something is linearly independent, right? Well, what you do is you set up your vector equation, right? Something is linearly independent is you set up your vector equation, right? So you have C1 times your first vector, C2 times your second vector, and so on, right? In this case, I just have two vectors. Set that equal to the zero vector, right? Okay, and then you solve the system, right? And if you solve the system, when you solve the system, if you get the unique zero solution, right, for C1 and C2, right? Okay, then that means, in other words, if the C1 must be 0 and the C2 must be 0, then that means that these vectors here are linearly independent, right? Okay, so I have this vector equation and I need to solve it, right? Okay, so how do I solve this, right? Well, what you do is you multiply, right, the C1 by these entries and the C2 by these entries, and you add, right? Okay, so let's do it component by component, right? What I'd have is C1 times 1, which is C1, and then C2 times 0, which is 0, right? So for the first component, I'm just going to have C1 on this side, and on the first component on the right hand side, I'm going to have 0, right? So looking at the first component, I get C1 is equal to 0, right? So I get C1 is equal to 0. And now you do the same thing for the second component, right? The second component over here for this one is 0, right? Second component for this product over here is C2, right? So I have 0 plus C2 is equal to 0, right? Okay, and I keep going like that, right? So the third component would give me the third equation. I get C1 over here, 1 times C1, which is C1. And then C2 times minus 1, which is minus C2. So I have C1 minus C2 for my third component over here, which is equal to 0, right? And then finally, by considering your fourth component, you're going to have 3C1 plus 2C2 is equal to 0, which is this, right? So this vector equation is actually equivalent to this linear system over here, right? And if you have this linear system, you could actually work backward and get this vector equation, right? The main thing is you just want to come forward, right? So given your vector equation, we have this system here, right? And now what we want to do is we want to solve the system, right? And this system over here is a homogeneous system. And you want to remember, a homogeneous system would always be consistent. It would always have the zero solution, right? The question is if that is the only solution, right? And that is actually the case, right? You see in that the C1 has to be 0 and the C2 has to be 0, right? Okay, so just this over here, right, is good enough, right? Okay, the C1 and the C2, they must be 0, right? This over here is not giving me any extra information and so on, right? All the information about the solutions of the system is coming from this over here. The fact that the C1 is 0 and the C2 is 0, right? And notice how clean this is, right? This is just simply telling me exactly that what I want for the linear independence, right? That the C1 is equal to 0 and the C2 is equal to 0, right? And why this is so clean is because if you're looking in the first component for your row vectors, you're going to get a C1 over here and you're going to get 0 over here, right? Now notice what it is, right? It's C1 times this row vector and then C2 times this row vector, right? Okay, so you'd always just have the C1 over here and everything else in the first component would just be 0, right? Because the C2 times 0 would give me a 0 over here, right? So the fact that I have just, this is RREF, right? And I just have this pivot over here in, it is the only non-zero entry in this column, right? That means that I will just get a nice clean equation with C1 is equal to 0, right? Okay, and likewise from the second column over here, right? The fact that this is a pivot and everything else is 0, right? In this column over here means that when I consider this vector equation with the rows, right? For my second component over here, right? I'm gonna have C1 times 0, which is C1 times the 0, C2 times 1, which is C2 times this one over here, which is C2, right? And then that's going to be equal to 0, right? Okay, so the fact that I just have this 1 over here as the only entry, non-zero entry in this column, right, gives me that the C2 is equal to 0, right? Okay, and in general, that is what is giving you your linear independence in these for an RREF, right? So if you have an RREF, right, and you consider in the rows, right, okay, and you form a vector equation with the rows, what you're really looking at is you're looking at the pivots, right? And with these pivots over here, what you would get is you'd always just get equations like these, right? C1 is equal to 0 and C2 is equal to 0. If I had a third row over here that was non-zero, right, and it was RREF, right, what I would get is C3 is equal to 0, right? So the independence of the non-zero rows of the RREF, right, it really comes from, you can easily see it from the fact that that this matrix is RREF, right? And because these columns have this sort of nice structure where at the pivot location it's the only non-zero entry, right? Okay, so I have this RREF. I look at the rows over here to show that the rows are linearly independent. I form this vector equation, and I said this vector equation, because of the form of this matrix, I'd always just have something like C1 is equal to 0 and C2 is equal to 0. And once you have a vector equation where these constants, when you solve, the constants must be 0, right? Then that tells you that these rows over here are linearly independent, right? Okay, so this is an example of what Theorem 3.4 is saying, right? I have a non-zero matrix that is RREF, right? So this is a non-zero matrix that is RREF, right? Okay, and if I have this RREF, right, and I look at the non-zero rows, which would be these two first rows over here, right? So first row, second row here, then these rows are linearly independent, right? Right, so for this example, matrix B over here, I showed that the non-zero rows are linearly independent, right? And now there's this next statement here that your non-zero rows are going to form a basis for the row space, right? Okay, so let's use this example to understand, see if we can understand what's going on, right? Okay, so what's the row space of this matrix B, right? Well, it's the span of all the rows, right? So it's span of the 3 rows here, right? Okay, so I have first row vector coming from first row, second row vector coming from the second row, third row vector, which happens to be 0 vector over here, right? So I take the span of those, which is all linear combinations of these 3 vectors, right? Okay, but what you want to notice, and this has to do with the fact that I'm looking at non-zero rows, right? What you want to notice is that this 0 row over here, right? This 0 row vector, when I multiply it by C3, would still just be a 0 row vector. And when I add it to these 2 over here, well, this one isn't going to contribute anything, right? Because 0 plus whatever this vector is, the sum of these 2 vectors is just going to be the same thing, right? So this one does not contribute anything for me, so I could really just drop it off, right? And I can drop it off, which means that I no longer need it, and I'd actually no longer need the C3 as well, right? Okay, so what I see is that the row space of B, right, I started off with these 3 vectors, but the fact that this one was a 0 vector means that I could actually drop it off, right? And what I'm doing is right, so I can drop it off, right? And when I drop it off, what I actually have is I have the span of the 2 non-zero vectors, right? So the span of the 3 vectors, including the last 0 vector, right? That last 0 vector I can drop off, right? Okay, so the row space, which is the span of the rows, right? I can drop off the 0 rows, and therefore the row space of B is just the span of the non-zero rows, right? Okay, so what do I have, right? This matrix B is RREF, right? I showed that the non-zero rows are linearly independent up here, right? And I just showed that the non-zero rows will span, right? Because the zero rows will not do anything for me in terms of span, right? Okay, so the non-zero rows, they span the row space, right? And then the non-zero rows are linearly independent, right? So these two non-zeros are linearly independent. And therefore, what that means is because they span the subspace and they span the vector space, and the fact that they're linearly independent means that they're going to be a basis for a row space of P. Right? Alright, so let's look at this this corollary, which means a consequence of the above theorem, right? Okay, so I have some matrix A to start off with, right? Such as this one over here, right? And the matrix A is necessarily RREF, right? Okay, so what this is saying, so I have an A over here, and then the B, for given some matrix A, now what you want to do is you want to consider matrix B that is row equivalent to A, right? In other words, given the A, you're going to apply Gauss-Jordan until you get an RREF B, right? So that's what happens here, right? I have a matrix A over here, and then I apply my RREF. I apply my Gauss-Jordan, right, to get an RREF matrix over here, which is B, right? Okay, alright. Okay, so what is this corollary saying, right? It's saying that the non-zero rows of B form a basis for the row space of A, right? Okay, so, well, why is that, right? We just saw that for this example, right, a matter of fact, it's the same matrix, right, that the non-zero rows would form a basis for row space of B, right? But this is saying something a little different, right? It's saying that the non-zero rows would form a basis for the row space of this one, the matrix A, right? But let's just remember what I had from a little earlier, right, is that I know that A and B are row equivalent, right? Because I got from A to B by doing row operations, right? So A and B are row equivalent, right? Which means that they have the same row space, right? Okay, so I know that from the example that I just did, that the non-zero rows of B would form a basis for the row space of B, right? But from this theorem over here, row space of B is actually equal to row space of A, right? So the non-zero rows over here, right, would actually form a basis for the row space of A, right? So that is what this is saying over here, right? The non-zero, if you have a A and you apply your Gauss-Jordan to get a B over here, your non-zero rows over here would form a basis for the row space of your original matrix, right? So we saw that if we have a matrix A, we could construct the row space by taking all possible linear combination of the rows, right? Such as this here, right? Okay, so this, we want to remember that when you take linear combinations of vectors, right, what you get over here is you're going to get a vector space, right? And this vector space over here, any vector space would have a dimension, right? Okay, so if I have my matrix A, I take the rows, I form the row space, right? The row space is a vector space, and the dimension of that row space has a certain name, right, which is called the rank, right? Okay, so that is the rank of your matrix A, right? So rank of a matrix A is the dimension of its row space, right? Okay, so let's see an example of calculating the rank of a matrix, right? So here I have this matrix A over here, right? And to get the rank, I would need the dimension of its row space, right? Okay, but I just saw that the row space of okay, so if I have A, I can apply Gauss-Jordan to get the matrix B, right? And the non-zero rows of the RREF over here would form a basis for the row space of B, right? And the fact that A and B are row equivalent means that the row space for B is the same as the row space of A, right? And that means that the non-zero rows here, these two non-zero rows listed over here, right, would form a basis for the row space of A, right? Okay, so the basis for row space of A consists of these two vectors, right? And the dimension of a vector space is the number of elements in the basis, right? Okay, and you see in this basis over here has two elements in it, right? So therefore the dimension of my row space of here is equal to 2, the number of elements in this basis, right? And dimension of row space is equal to rank, right? So rank of this matrix A over here is in fact equal to 2, right? So that's what's said over here, right? Okay, now a little more generally is this statement here in Corollary 3.5, right? If I have a matrix A such as this one, right, and I apply Gauss-Jordan to get an RREF B here, right, then the number of non-zero rows of the RREF here, right, is equal to the rank of my original matrix, right? Okay, and this would be something that you most likely would have seen before, right? And you probably know this as your definition of rank, right? Which isn't quite correct, right? So if you have a matrix A, you probably learned from 1180 to get the rank. What you do is you apply Gauss-Jordan to it, right? So to get a matrix like this, and then you count the number of non-zero rows, and that will give you the rank, right? Okay, and that's correct, right? But that's not your definition of rank, right? The definition of rank is if I have a matrix A, I form the row space of it, right? And then the dimension of the row space is equal to the rank, right? It just so happens that that same rank is equal to the number of non-zero rows of the RREF, right? Right, okay, so let's talk about column space now, right? So we talked about row space, right? What row space was is row space was taken all possible, you take your rows and take all possible linear combination of row vectors formed from the row, right? Now column space, well, you're just doing the same thing basically for columns, right? So I have some m by n matrix such as this one over here, right? So it's the same matrix actually in this example, right? And now what I do is I take the columns of this matrix, right? So the columns of this matrix would be 1, 0 over here and 2, 1 over here, right? So first column is 1, 0, second column is 2, 1, right? And your column space of the matrix would be all possible linear combinations of your columns, right? So I have first column here, second column here, so all possible linear combination of these two column vectors would be C1 times 1, 0, C2 times this 2, 1 over here, so second column, where the C1 and C2 could be anything over here, right? Okay, right, so this is an example of column space of this matrix here, right? And the dimension of the column space of A is called the column rank of A, right? So this, when I take the span of these two column vectors, right? Whenever you take the span of any vectors, you get a vector space, right? Okay, so the span of these two column vectors gives me a vector space, and because it's a vector space, I can consider the dimension of it, right? And the dimension of this particular vector space, which is column space, is called column rank, right, of your matrix A, right? And we will see later on that your column rank is actually equal to the rank that you get from the row space, right? Okay, it takes a little bit of work to show that, right? But column rank is actually just going to be equal to rank of your matrix A, right? But for the time being, column rank is dimension of the column space, right? Right, okay, so let's notice some basic things about multiplying a matrix against a vector, right? Okay, so here I have a m by n matrix, capital A over here, right? And I have this vector here, x1 to xn, right? So I notice my matrix multiplication is conformable in this case, right? This is a m by n matrix, and this is a n by 1 column vector, right? So the n's match, right? The number of columns in this matrix, the number of columns in this matrix is equal to the number of rows, right? Okay, and you all know how to multiply this matrix here by this vector over here, right? And the working, if you want, is here, right? Okay, so to multiply this matrix by this vector, you take your first row here and you multiplying it against your vector here, right? So it'll be A11 times x1, A12 times x2, and you keep going like that, A1n times xn, and you're going to add all of those up, right? Okay, and then likewise you take your second row, multiply it against this vector over here, and you'll get a sum again, right? And you do that for each of your rows here, right? So finally you have this last row, and you're going to multiply against this vector over here, right? So you'll get this sum there, right? Right, so this is something that you would have known, right? This line here you would know, right? What I want to note is you can actually write this in a different way, right? You can think of this matrix multiplication in a different way, right? So this is equal to this, but let's consider this equality sign now, right? Okay, so what do I have over here, right? What I have is x1 times this column vector, right? And what this column vector is first column, right? And then I have x2, which is this column vector against this column vector, which is the second column of my matrix A, right? And I'm saying that x1 times this vector plus x2 times this vector plus xn up to xn times this vector is actually equal to this sum, right? And that's not hard to check, right? You could just really look at the components, right? What's the first component from this vector sum, right? What you have is x1 times a1 plus x2 times a12, right? Okay, so x1 times a11 plus x2 times a12 plus xn times a1n, right? Which is this first component here, right? And then your second component is x1 times a21 plus x2 times a22 up to xn times a2n, right? Which is the second component over here, right? So you see, if you multiply this x1 times this vector and x2 times this vector and xn times this vector and you add them up, right, all you're going to get is you're just going to get this here, right? And this in fact is a times x, right? Alright, so the point that I want to make over here, and this sometimes is useful, right, that if you have a matrix A and you're multiplying it against a vector x, right, one sort of fast way to do it is you take x1 times the first column, and then you take x2 times the second column, and then up to xn times the last column, and then each of these are vectors, so you'll take x1 and multiply by this vector, x2 multiply by this vector here, xn multiply by this vector, and when you add them up you'll get the result of the matrix multiplication, right? Or if you want, you could do this matrix multiplication, this a times x, by taking x1 times first column, x2 times second column, xn times last column, right? And then you add all of those up, and that would be equivalent to doing this matrix multiplication. Right. Okay, so let me review a little more matrix vector multiplication. So I'm multiplying a matrix against a vector, right? Okay, so what I have over here is, this is a matrix here, m by n matrix, and these are n by 1 column vectors, right? And what you're doing here is you're adding the x and y 2 column vectors together, these of the same size, right? So you add them together and then you multiply by a, right? Right, and what this equation is saying is that the matrix multiplication over here distributes over the addition, right? So I can work this out by multiplying the a times the x first, right? A times the x, then multiply the a times the y, and then add those, right? So on this side, what you're doing is you add the two vectors first, and then you multiply by a. Right? On this side over here, you take the x, multiply by a, you take the y, multiply by a, and then you add, right? And you get the same answer in both cases, right? And I'm sure you've seen that before, right? Okay. Now the proof of this is you can use this, the idea of your matrix multiplication, as being you take your vector over here and you take scalars from the vector and you multiply against each column, right? So I can use this statement here, this way to view the matrix multiplication to prove this, right? And is in fact done in the notes, right? Okay, so Now the second sort of matrix vector multiplication that I want to look at is, here I have vector x over here, and I'm going to multiply by a scalar here c, right? So scalar times the vector x, right? So I work this out first, and then I multiply by a, right? And it turns out that that is equal to, if I take the x and multiply by a first, right? And then multiply by c afterwards, right? Okay. Right, so let's continue with some sort of basic facts here, basic review, right? Right, so if I have a linear system, such as this one here, right, I can write it in matrix form as Ax is equal to B, right? Where the A is called your coefficient matrix, right? And your coefficient matrix is coming from the constants in front of the variables x1 to xn, right? Okay, the x here is a variable of a vector of variables here, right? So the x1, x2 up to xn would form this vector over here, right? And then the scalars on the right hand side over here would form this constant vector b here, right? Okay, so again, any linear system I can write as a matrix equation, Ax is equal to b, right? And if you want an example of this, right? Okay, so here I have a linear system in variables x, y, and z, right? And you can write this as in matrix form, Ax is equal to b, right? So your matrix A is coming from your coefficients, say 5, 15, and 56. It's from your first row over here. The variable, the vector of unknowns, right, is a vector consistent of the unknown variables, which are the x, the y, and the z over here. And then the constant vector is coming from your right hand side of this system here, right? So the 35 minus 26.5, right? This is typed a little badly. You really shouldn't have any large spaces over here, right? Okay, so this is an example of writing a system as Ax is equal to b, right? Well, I'm saying that if I have a linear system, I can write it as Ax is equal to b, and let's actually see that, right? Why you can do that. Okay, so I have Ax is equal to b, and I'm going to show that you can write it as a linear system, or given a linear system, you can go backwards and write it as Ax is equal to b, right? And this isn't really a big deal, right? Okay, so I have my matrix A, I have the vector of unknowns, and I have my constant vector here, right? So what I do is, given this Ax is equal to b, I do matrix multiplication on the left hand side, right? And I'd get a11 times x1, a12 times x2, keep going, a1n times xn. So I'm just multiplying out, right? Okay, so on my top entry over here, right, I have a11 times x1 plus a12 times x2 plus a1n times xn, right? So in other words, just this row multiplied against this column vector over here, right? You want to notice that this here, this is a vector, right? And this also is a vector, right? Okay, so now, so that's how you're going to get your first row over here. And this first row, because you have an equality, this first row over, this first entry over here is equal to the first entry over here, right? And likewise, this second entry over here is equal to the second entry, right? Okay, so because your first entry here is equal to this first entry here, right, the b1, right, you get an equation here, right? Likewise, second entry over here is equal to this b2 here, so you get a second equation, right? So for each of your rows here of your vector, right, you're going to get a corresponding equation, right? And this is your linear system, right? So we just showed that given the Ax is equal to b, you can get a linear system, right? And given the linear system, you could really just go backwards to get the matrix Ax is equal to b, right? Okay, so if you have your linear system, each equation would form an entry in the vector, so entry in the inner vector equation. So for example, for this linear system over here, if you look at the first equation, you look at the left hand side, so the left hand side would be your first entry in this vector, and the right hand side, the b1, would be the corresponding first entry in this vector over here, right? So likewise, this would form second entry in your vector, and the b2 would form the second entry in the vector, right? So you build up a vector using the left hand side over here, and you build up a vector using the right hand side of your system here, right? Okay, and then what you want to realize is that this is actually matrix multiplication of this matrix over here against this vector x1 to xn, right? So I rewrite this sum over here, right, where each entry here is a sum, right, as matrix multiplication, and this gives me the Ax is equal to b, right? But the main thing I want you to get out of this is your linear system of linear equations. You can write as a matrix equation, which is Ax is equal to b, right? So if I have a m by n matrix here, what I can do is I want to consider this matrix equation, which is Ax is equal to 0, right? And your solution set of this matrix equation, right? So set of solutions of this matrix equation, or equivalently, what you could do is you could just multiply everything out, right? So if you have the Ax is equal to 0 over here, you can just multiply it out and you'll get a system here, right? So multiplying out this matrix equation gives me a homogeneous linear system, right? It's homogeneous because your right hand side is a 0 vector here, which means that I have zeros on the right hand side here, right? Okay, so solution set of this matrix equation, or equivalently the solution set of this linear system, right? Alright, so given a matrix A, right, solution set of its matrix equation, or equivalently the solution set of the corresponding homogeneous linear system, that solution set is called the null space of the matrix A, right? And it's denoted by this cursive n here, A, right? So n here means null space, right? So this means you could read this as null space of matrix A, right? Okay, so your null space is a subspace of R to the Rn, right? Well, why is that? Well, the solutions would be, any solution would have to satisfy, for example, this linear system, which means that you need a value for x1, a value for x2, and a value for xn, right? And what you're doing is you're assembling that as vectors, right? So we'll see in a second why it's a solutions, a subspace of R to the n, right? And the next thing is this solution set is a subspace, right? And it has a specific dimension. The dimension is n minus rank of A, right? And we saw already how to calculate rank of A, right? How you calculate rank of A is you apply Gauss-Jordan to A, get the RREF matrix that we call B, right? And the number of non-zero rows of that RREF is equal to the rank of A, right? Okay, so the null space of this of your matrix over here A is solution set of this matrix equation, right? And it's going to be a subspace of Rn, right? And it has dimension n minus rank of A, where the small n is the number of columns of A, right? Okay, so let's take a look at an example of calculating null space of a matrix A. Alright, okay, so let's get the null space of this matrix B over here, right? So this is a 2 by 4 matrix here, right? Right, so this particular problem is from your 2013 past paper, and this is posted on the course website. And the solution here for your past paper is also posted on the course website, right? Okay, so we have this matrix B and we want to get the null space of it, right? Okay, so, well, what is null space? Null space is the null space is the solution set of your matrix equation Bx is equal to 0, right? Where x is a vector of unknowns, right? Or equivalently, as we just saw, you can multiply this out to get a system over here, right? A homogeneous system, right? Okay, so in null space of your matrix, B is solution set of this matrix equation, or equivalently, it's a solution set of the homogeneous system that you get by multiplying out, doing your matrix multiplication here on your on your left hand side, and then just taking the equations from that, right? Okay, so what we want to get is solution set of this homogeneous system, right? And to get the solution set of this homogeneous system, we know how to do this already, right? We've seen this before, right? What you're going to do is you're going to form, you know, augmented matrix, right? Now with this augmented matrix, notice the right hand side over here is 0, right? And when you start doing your row operations on this augmented matrix, right, this right hand side would always remain 0, right? If you multiply, say for example, this row over here by a half, right, to make this 1, right, that would still remain 0, right? If you switch rows, you're still gonna have 0 in this column over here, right? Okay, and if you add a multiple of one row to the next row, this column of zeros is not going to change, right? So because of that, if you're doing this sort of problem, right, where it's homogeneous, right, you do not necessarily need to write down the zeros on this right hand side, right? So that's actually what I do in this solution here, right? I have this augmented matrix, and how you go about solving this system here is you apply Gauss-Jordan, right? But the point that I want to make is in the solution, I didn't write down the zeros here for the constants, right, for the right hand side, right, because you don't really need to for a homogeneous system, right? Anyway, so I have my my matrix, right, and then what I'm going to do is I'm going to apply Gauss-Jordan to it, right? So you apply a Gauss-Jordan, and the details about the Gauss-Jordan algorithm, the actual row operations in the solutions, right? Okay, and when I do my row operations, I get this RREF matrix here, right? Okay, so this RREF matrix here, right, is associated. This has a corresponding system, right? So this over here, this matrix to start off with was associated to this homogeneous system, right? Okay, and this RREF over here is associated to this homogeneous system, right? Okay, so you take your matrix entries over here, and these are going to form the coefficients of the system, right? Okay, and we should know by now that when you apply row operations and you form this corresponding system, the row operations are not going to change the solution set, right? So the solution set of this system over here is the same as the solution set of this system over here, right? Okay, so now that I have this, right, let's get the solutions, right? Okay, so you want to notice that I have two pivots over here. This is one pivot here, and this is my second pivot, right? The variables that I'm using are x1 to x4, right? Okay, so I have a pivot in column 1, so I'm going to have pivot variable x1. Okay, I have a pivot in column 2, so I'm going to have pivot variable x2, right? So x1 and x2 are pivot variables, which means that everything else is going to be a free variable, right? Okay, so in this system over here, once this is RREF and this is the associated system, right, it means I can express the pivot in terms of the free variables, right? Okay, so all you need to do is just move your free variables across to the right hand side, right? So that's what you do over here. And notice I have x1 in terms of free variables and x2 in terms of free variables, right? Okay, so what is going to be a solution set, right? The solution set is going to be x1, x2, x3, and x4. That satisfies this, right? But if it satisfies this system labeled as 1 over here, it means that the x1 is equal to these free variables and the x2 is equal to these free variables, right? So while this is x1, x2, x3, and x4, right, you replace the x1 and x2 by the expression with free variables here. And remember, these are free, right? So the x3 and x4 could be anything here, right? And notice this actually is the solution. This is in fact a null space, right? But we want to write it in a better way than this, right? Okay, so notice what you can do is you can separate over here the x3. So you're going to have a minus 6 on 5 x3 minus 1 on 5 times x3. You're going to have an x3 and you have no x3 over here, right? And then likewise, you're going to have terms in x4 across here, right? Okay, so you can break your vectors into just break this single vector into two vectors, one with x3 alone and one with x4 alone. And then once you have that, you can factor out the x3 and you can factor out the x4, right? Okay, so this over here, this is your solution set of this system over here, and therefore it's a solution set of this system over here, right? And because it's a solution set of this system, it's a solution set of this matrix equation, right? And therefore, and the solution set of this matrix equation by definition is a null space of the matrix B, right? So this here, this is my null space of B. So the second part of the question here is to calculate the dimension of the null space, right? And we have a formula here for dimension of null space, right? Dimension of null space is n minus the rank of a matrix A, right? So dimension of null space of A is n minus rank of A, right? Okay, so let's work it out in this case, right? Here the matrix is called B, right? So what I would need is n minus rank of B, right? Right, so the dimension of the null space of the matrix B is n minus rank of B, right? And well, what's rank of B, right? We saw already how you can get rank of B is you apply Gauss-Jordan to this matrix B, you get RREF, right? And then you count the number of non-zero rows in that RREF, right? So that is what this is saying here, right? The rank of B is the number of non-zero rows in the RREF that is row equivalent to B, right? In other words, the RREF when you apply Gauss-Jordan to B, right? Okay, so well, the B was what? The B was this matrix over here, right? The B is this matrix over here. When we applied Gauss-Jordan to it, we got this matrix over here, right? So this is an RREF, right? And you want to notice the number of non-zero rows over here is equal to 2, right? Okay, so the dimension in the null space, which is n minus rank of B, which is n minus the number of non-zero rows of the RREF, right, is 2, right? So this n is the number of columns. So the number of columns that I have over here is 1, 2, 3, 4. So number of columns, small n, is 4, right? Number of non-zero rows is 2, right? 2 over here in the RREF, 2 non-zero rows. Okay, so what I get is 4 minus 2. So the dimension in the null space is 2, right? Okay, so that's how you would actually calculate it, right? You can in fact see it over here too, right? Your null space is how this is written. This is the span of these two vectors here, right? This vector over here and this vector over here, where you're free to choose whatever x3 and x4 that you want, right? And these two vectors are linearly independent, right? Okay, right? Because if you can check, because the ones and zeros, the location of the ones and zeros over here, right? Or a next way to realize this vector is not a multiple of this vector over here, right? So these two vectors are linearly independent, right? So what you have is this is the span. This what we have over here for my null space of B is the span of these two vectors. These two vectors are linearly independent. So these two vectors, they span in the null space by construction, right? And they're linearly independent, right? Which means that these two are going to form a basis for your null space. And the amount of elements in your basis is going to be equal to the dimension in null space. And you notice that you have 2, right? Okay, so the fact that I have 2 vectors over here agrees with this answer here. This 2 over here, right? Right, so let's see how if we can get an idea of where your formula for dimension of null space comes from, right? Okay, so dimension of null space is n minus rank of A, right? So where does that come from, right? Okay, so let's notice that in order to get the null space, and we'll use this example for your matrix, the matrix B, right? Which is matrix B is, this is your matrix B over here, right? Okay, in order to get null space of this, right? Okay, and what we want to look at is the formula for dimension of null space is supposed to be n minus the rank of the matrix B, right? Okay, so, well, what was the null space? The null space was a solution set of the associated homogeneous system, right? Okay, so the null space is a solution set of this homogeneous system over here, right? Okay, and when we found the solution of this homogeneous system by using Gauss-Jordan and figuring out what your free variables were, right? What we did is we wrote the solution set in terms of the free variables, right? Notice here I have pivots x1 and x2. I express the x1 and x2 in terms of free variables here, right? And so the solution set, which is x1, x2, x3, and x4, where the x1 is expressed in terms of free variables and the x2 is expressed in terms of free variables, right? So this solution over here is expressed in terms of two variables, x3 and x4, right? And we talked about, I said that what you could do is you could separate these. You have a vector just in this single vector here, you can separate into a vector just involving x3 and a vector just involving x4, right? And once you do that, you could pull the x3 out of your first vector and x4 to the second vector, right? Okay, so your solution set would have a vector here for each of the free variables, which are x3 and x4, right? Okay, so, and that is true in general, right? Okay, so when you have a matrix B and you form your associated homogeneous system, you get your solution set, right? And the solution set is expressed in terms of the free variables, right? The solution set, what you'd have is you'd have a basis vector for each of your free variables, right? Okay, so what that is saying is that the dimension of the null space is in fact equal to the number of free variables, right? Okay, and in this case the number of free variables is 2, right? Anyway, so going with that idea, I have the dimension of the null space is equal to the number of free variables, right? Okay, but what is number of free variables, right? Number of free variables. Well, the number of free variables plus the number of pivot variables is equal to the total number of variables, right? Okay, so which means that the number of free variables is going to be equal to the total number of variables minus the number of pivot variables, right? So you have 4 total number of variables, which would be the x1 to x4, right? And that is actually equal to the number of columns that you have in this matrix, right? Okay, so the number of free variables is total number of variables minus the number of pivot variables, right? Now it turns out the number of variables that you have, right? You have a variable for each one of your columns in the matrix, right? Because when you set up, when you have a homogeneous system over here, right? And this is the matrix B, right? Notice you have 1, 2, 3, 4 columns over here, right? And forming this system Bx is equal to 0, right? What you're going to have is you're going to have a variable for each column, right? Okay, so the number of total number of variables is actually equal to the number of columns, right? And that is equal to the small n over here, right? And the number of pivot variables, well, what's the number of pivot variables? The number of pivot variables, once you doing this working with the RREF, right? The number of pivot variables, you're going to have a pivot variable for each non-zero row, right? Okay, so your number of pivot variables is actually just equal to the number of non-zero rows of the RREF, right? This pivot variable is for this non-zero row. This pivot variable is for this non-zero row, right? Okay, so what I have is number of columns minus number of non-zero rows of the RREF, right? But the number of columns I just said was equal to small n over here. And the number of non-zero rows, we saw already that if I have a matrix, I apply Gauss-Jordan and I get an RREF, the number of non-zero rows of this, right, is equal to the rank of this original matrix, right? Okay, so this number of non-zero rows is equal to rank of the matrix, so I therefore get dimension of my null space is equal to n minus the rank of the matrix, right? And that is a summary of really the theorem in the notes, right? So the theorem in the notes, right, that says that if I have a matrix A, right, then the dimension of the null space is n minus rank of A, right? Okay, the proof of it is in the notes, but really the proof of it is using this idea over here, right?